learning objectives. In this chapter, the user will learn the following in detail: regularization theory, optical computation, motion estimation, structure from motion. Introduction of motion field. When an object moves in front of a camera, there is a corresponding change in the image. If a point P0 on the object moves with the velocity V0, then the image point Pi can be assigned a vector Vi to indicate its movement on the image plane. The collection of all these vectors forms the motion field. This figure shows the motion field of a moving square. In the case of pure camera translation, the direction of motion is along the projection ray through the image point from which or towards which all motion vectors radiate. The point of divergence or convergence of all motion field vectors is called the focus of expansion, FOE, or focus of contraction, FOC. Thus, in the case of divergence, we have forward motion of the camera, and in the case of convergence, backwards motion. Motion analysis. Motion analysis is used in computer vision, image processing, and high-speed processing. Motion analysis processing can be, in the simplest case, be to detect motion, that is, find the points in an image where something is moving. 3D motion between observer of the scene and the structure of the scene. Two static points close by in the image with different image motion. The larger translational motion corresponds to the point closer by, smaller depth. Motion analysis requires the storage and manipulation of image sequences rather than single images. Image sequences can be stored as list of arrays, vectors of arrays, or 3D arrays. Each image in a sequence is often called a frame, and the time which elapsed between each frame being digitized, the frame interval. The inverse of the frame interval, that is the number of frames per second, is a frame rate. Applications of motion analysis: surveillance, medicine, film industry, automotive crash safety, ballistic firearm studies, biological science, flame propagation. Motion analysis. Motion analysis is dealing with three main groups of motion-related problems: motion detection, moving object detection and location, derivation of 3D object properties. Motion analysis and object tracking combine two separate but interrelated components: localization and representation of the object of interest, target, trajectory filtering, and data association. One or the other may be more important based on the nature of the motion application. Motion detection and tracking. To detect and track objects moving independently to the background. Two situations encountered are static camera, fixed viewpoint, moving camera, move viewpoint. Definition of motion detection: action of sensing physical movement in a given area. Motion can be detected by measuring change in speed or vector of an object. Applications of motion detection and tracking. Surveillance, monitoring applications. Security cameras, traffic monitoring, people counting. Control applications, automatic guidance, head tracking for video conferencing. Many intelligent video systems are based on motion detection and tracking techniques. Detecting moving objects in a static scene. Moving objects can be detected by using background subtraction algorithm. Frame differencing. Simple method. Subtract consecutive frames. Ideally, this will leave only moving objects. Following conditions affect the background subtraction. Moving background, example, swaying of trees. Temporarily stationary objects, object shadows, illumination variation. Background subtraction. Motivation. Simple difference. Frame simple difference of two images shows moving objects. Uses a reference background image for comparison purposes. Current image containing target object is compared to reference image by pixel. Places where there are differences are detected and classified as moving objects. Background subtraction methods. Background as the average or the median. Velastine 2000, Kukiara 2003 of the previous n frames. Rather fast but very memory consuming. Memory requirement is n into size of frame. Background as the approximate median filtering, AMF, running average is shown on the screen. Background as the approximate median filtering, AMF, running average, BI plus 1 equals alpha into LI plus 1 minus alpha into BI, where alpha, the learning rate, is typically 0.05, no more memory requirements. The background model at each pixel location is based on the pixel's recent history. In many works, such history is just the previous n frames, a weighted average where recent frames have higher weight. In essence, the background model is computed as a chronological average from the pixel's history. No spatial correlation is used between different neighboring pixel locations. Gaussian mixture model of BSMN. Gaussian mixture models. Each pixel modeled with a mixture of Gaussians, flexible to handle variations in the background. An example is shown on the screen. All weights WI are up, updated and or normalized at every new frame. At every new frame, some of the Gaussians match the current value, those at a distance less than 2.5 sigma I. For them, mu I, sigma I are updated by the running average. The mixture of Gaussians actually models both the foreground and the background. How to pick the distribution models at the background? All distributions are ranked according to their omega I by sigma I, and the first one is chosen as background. 2 tasks performed real time. Classifying pixels as background or foreground, learning the background model. The parameters of Gaussians: mean, variance, and weight. Number of Gaussians per pixel. Enhanced GMM is 20% faster than the original GMM. Classifying pixels. X vector power t equals value of a pixel at time t in RGB color space. Bayesian decision R, if pixel is background or foreground. R equals probability of background given x vector power t over probability of foreground given x vector power t equal to probability of x vector power t given background into probability of background over probability of x vector power t given foreground into probability of foreground. Initially, set probability of foreground equals probability of background. Therefore, if probability of x vector power t given background is greater than C threshold, decide background probability of x vector power t given foreground equals C foreground. Probability of x vector power t given background model. P cap of x vector given chi, bg equals estimated model based on the training set chi. The GMM model. Choose a reasonable time period t, and at time t we have chi t equals x to the power t going up to x to the power of t minus t. For each new sample update the training data set chi t. Re-estimate p cap x vector given chi t, background. Full scene model of background plus foreground is shown in the equation on screen. In this equation, GMM with m Gaussians where mu1 vector cap going up to mu m vector cap estimates of the means, and sigma 1 cap going up to sigma m cap represents estimates of the variances. Pi m cap represents mixing weights non-negative and add up to 1. Object tracking. Object tracking is a crucial research issue in computer vision, especially for the applications where the environment is continuously changing. Robot vision. Mobile robot navigation. Applications that must deal with unstable grasps. Surveillance. Traffic applications. Human motion capture. The most common approaches for object tracking are based mainly on the detection of one of the following cues: edges, color, or texture. Concerns the extraction of a number of features of the object: points, lines, distances, models of the contours. These features allow to have fast tracking process and also to estimate the pose of the object. This is generally based on the analysis of the gradient's intensity. Color. When color is the main different characteristic of the object in relation with the environment, extraction of several characteristics based on different color spaces, RGB and HSI, have been proved to be efficient for situations where the light conditions are not uniform and are changing during the tracking procedure. HSI color space. Texture. Recent research application field. Used to object tracking, especially as a complement to a multi-cue tracker. The most common texture segmentation techniques tend to be computationally intensive and use classification methods that require a time-expensive offline learning phase. For these reasons, such approach isn't consistently used for tracking purposes. Typically, application has to deal with the following main problems: the clutter environment, specifically non-uniform light conditions and different objects with the same color pattern, the presence of the object at different distances relative to the camera during the tracking procedure, real-time processing, image noise. Color tracker, camshift. Camshift algorithm, continuously adaptive mean shift, camshift. Camshift algorithm, RGB image. Convert RGB image to HSV. Initial search window. Set search calculation region larger than search. CalC color histogram model. CalC color probability distribution image. Set search window. Find center of mass within the search window. X, Y, area. Center search window at the center of mass and find area under it. Converged. Yes, no. Each video frame, the raw image is converted to a color probability distribution image via a color histogram model of the color being tracked. The center and size of the color object are found via the camshift algorithm operating on the color probability image. The current size and location of the tracked object are reported and used to set the size and location of the search window in the next video image. The process is then repeated for continuous tracking. Color tracking procedure. This algorithm uses a search window to track the moving object, ignoring objects outside the search window. Scales the search window to object size, thus allowing different distance between the object and the camera. The color space used is a HSV, which is less sensitive to lighting changes. The color model is mainly based on the hue histogram, which eliminates much of the noise present in the image. Cam shift algorithm. A problem can occur when using HSV space. When brightness is low, I near 0, saturation is also low, S is near 0. Hue then becomes quite noisy, since in such a small hex cone, the small number of discrete hue pixels cannot adequately represent slight changes in RGB. This then leads to wild swings in hue values. To overcome this problem, simply ignore hue pixels that have very low corresponding brightness values. With sunlight, bright white colors can take on an object hue, so use an upper threshold to ignore object hue pixels with corresponding high brightness. At very low saturation, hue is not defined, so also ignore hue pixels that have very low corresponding saturation. This means that the camera must auto-adjust or be adjusted for brightness. Motion estimation. Motion estimation examines the movement of objects in an image sequence to try to obtain vectors representing the estimated motion. Motion compensation uses the knowledge of object motion so obtained to achieve data compression. In interframe coding, motion estimation and compensation have become powerful techniques to eliminate the temporal redundancy due to high correlation between consecutive frames. Motion can be a complex combination of translation and rotation. Such motion is difficult to estimate and may require large amounts of processing. However, translational motion is easily estimated and has been used successfully for motion compensated coding. Motion estimation algorithm. Objects move in translation in a plane that is parallel to the camera plane, that is, the effects of camera zoom and object rotations are not considered. Illumination is spatially and temporally uniform. Occlusion of one object by another and uncovered background are neglected. Why is motion estimation needed? Denoising, compression, surveillance, depth estimation, super resolution. Denoising. Additive noise in video sequences can be removed by spatial and temporal filtering. A typical such filter applies a weighted average of the 3D neighborhood in order to compute the corrected pixel value. In applying temporal smoothing, the correspondence information is crucial for good performance. Denoising graphs are shown on screen. Image compression. In compressing video images, if we have already compressed function f of t minus 1, we know much about f of t. Typical approach, building a predicted image for f of t based on f t minus 1. Much better compression is achieved if we apply motion compensation. The screen shows examples of image compression. Surveillance. Motion estimation plays an important role in applications such as target tracking and movement change detection in surveillance systems. If the motion is a result of both camera and the image object's motion, these tasks are far more complex due to the need to decouple these motion fields. Depth estimation. Given a pair of images and the correspondence between them, depth of the imaged objects can be recovered. Depth is important for mapping digital elevation model extraction, segmentation to background, foreground, objects recognition, etc. Representation of depth estimation can now be seen on the screen. Super resolution. Given a set of low-quality images of the same object taken from slightly different locations, a better super-resolution image can be recovered. The recovery process requires a knowledge of the motion with sub-pixel accuracy. We can now see an example. A set of low-quality images is seen on the screen. Each of these images looks like this. After super resolution, we get the recovery result like this. The global motion equation is f of x, y, t equals f of x minus vx of x, y, t, y minus vy of x, y, t minus 1. The motion estimation problem is represented on screen. Motion representation. The possibilities are: define a motion vector for every pixel v of x, y, t. Define a motion vector for every block of m by m pixels. Assume global motion behavior and represent the motion by the parameters of the global mapping. Global motion assumption. In the general case, we assume the existence of the following relation. The function p is a simple relation that relates previous position to the current one. A set of parameters governs a specific type of motion. We can now see on the screen different representations of global motion. Global motion, translation, global motion affine, and global motion projective, and global motion estimation. Block motion estimation. If we are to find the motion by assigning a vector per pixel, then we have too many unknowns to be estimated, too much storage space is consumed, too much data to be transmitted, coding, ill-posed problem, too many unknowns. Solution: divide the image to blocks and assign a motion vector per each block. Steps for block motion estimation. Step 1. Divide the image f of x, y, t into non-overlapping blocks of m by m pixels. Step 2. For every block, we perform a search process in the previous image. F of x, y, t minus 1. For m equals 3, we obtain. Step 3. The search in f of t minus 1 is done by computing a matching factor to every possible displacement. Step 4. Choose a motion vector vx, vy, which results with the smallest error e. The basic assumptions in this process are: in the block matching algorithm, we assume that all the pixels in every block have the same motion vector. The above implies that the block is assumed to have global translational motion. We can assume a more general parametric model for the block motion, such as affine. Complexity in BSE. Search zone. Instead of computing E for every possible position in f of x, y minus t minus 1, we can assume minus d is less than or equal to vx and vy is less than or equal to plus d. This way, E is computed only 2d plus 1 into 2 times. Complexity error. Instead of defining the error E as a mean square error, define it as mean absolute differences as shown on the screen. Thresholding. Start by computing E of 0, 0, and if it is smaller than some threshold, assume no motion and do not continue. This can be represented as spiral search. Start from E of 0, 0 and compare E of U, V while computed to the minimum so far. If it is bigger, there is no need to continue. This can be represented as computing E, U, V at 9 locations around E 0, 0. Find the minimum point and compute 3 additional E rows, columns near it. Search the new minimum point. Applications. Block motion estimation (BME) is extensively used in video coding, MPEG-1, MPEG-2, MPEG-4, H.261, and H.263. Typically, blocks of 8 by 8 or 16 by 16 are used. In regular video coding, motion estimation consumes 50 to 80% of the CPU time. There are chips that perform BME. Optical computation. Optical computation of motion analysis. Optical flow reflects the image changes due to motion during a time interval dt, which must be short enough to guarantee small interframe motion changes. The optical flow field is the velocity field that represents the 3-dimensional motion of object points across a 2-dimensional image. Optical flow is the displacement field for each of the pixels in an image sequence. Optical flow computation is based on 2 assumptions. The observed brightness of any object point is constant over time. Nearby points in the image plane move in a similar manner, the velocity smoothness constraint. The basic idea underlying most algorithms for optical flow computation. Regard image sequence as 3-dimensional x, y, t space. Determine x and y slopes of equal brightness pixels along t-axis. The computation of actual 3D gradients is usually quite complex and requires substantial computational power for real-time applications. Let us consider the 2-dimensional case, one spatial dimension x and the temporal dimension t, with an object moving to the right. Instead of using the gradient method, one can simply determine those straight lines with a minimum of variation, standard deviation in intensity along them. Optical flow computation will be in error if the constant brightness and velocity smoothness assumptions are violated. In real imagery, their violation is quite common. Typically, the optical flow changes dramatically in highly textured regions, around moving boundaries, at depth discontinuities, etc. Resulting errors propagate across the entire optical flow solution. Global optic flow. Global error propagation is the biggest problem of global optical flow computation schemes, and local optical flow estimation helps overcome these difficulties. However, local flow estimation can introduce large errors for homogeneous areas, that is, regions of constant intensity. One solution of this problem is to assign confidence values to local flow estimations and consider those while integrating local and global optical flow. Detection motion pattern in optic flow fields. We can compute the local speed gradient to detect certain basic motion patterns. The speed gradient is defined as the direction of the steepest speed increase, regardless of the direction of motion. There are 4 different basic motion patterns: counterclockwise rotation, clockwise rotation, contraction, and expansion. Field point correspondence. Feature point correspondence is another method for motion field construction. Velocity vectors are determined only for corresponding feature points. Object motion parameters can be derived from the computed motion field vectors. Motion assumptions can help to localize moving objects. Frequently used assumptions include, like discussed above, maximum velocity, small acceleration, common motion. Optical flow estimation. 2D motion field. 2D velocities for all visible points. Optical flow field. Estimate of the 2D motion field. The image motion diagram can be seen on screen. A 3D point x vector follows a space-time path x vector t. Its velocity v vector is given by the equation on screen. Perspective projection for nodal length f of the 3D path onto the image plane produces a 2D path as shown. The instantaneous 2D velocity of which is optical flow. Two key problems: determine what image property to track, determine how to track it. Brightness constancy. More precisely, let's track point of constant brightness, assuming that surface radiance is constant over time. Brightness constancy is often assumed by researchers and often violated by Mother Nature, so the resulting optical flow field is sometimes a very poor approximation to the 2D motion field. Gradient motion estimation. Let f of x denote a 1D gray level function of spatial position and make the following assumption. F of x is translated by t between time t1 and dt2. We can express the shifted signal as a Taylor expansion of f1 about x as shown, in which case the difference between the two signals is given by. Then a first-order approximation to the displacement is. For linear signals, the first-order estimate is exact. For nonlinear signals, the accuracy of the approximation depends on the displacement magnitude and the higher-order signal structure. Gradient constraint equation. In two spatial dimensions, the first-order approximation is taking the time difference with times t and t1. Written in vector form, the following equations obtain. When the duration between frames is large, it is sometimes more appropriate to use only spatial derivatives in the Taylor series approximation. Thus, difference approximation, where gradient constraint equation can directly derive from brightness conversion. Let x of t and y of t denote a space-time path along which the image intensity remains constant. That is, the time-varying image f satisfies the equation f of x of t, y of t, t equals c. Taking the total derivative of both sides gives the following equations. The total derivatives is given in terms of its partial derivatives. Normal velocity. The gradient constraint provides one constraint in two unknowns. It defines a line in velocity space. The gradient constrains the velocity in the direction normal to the local image orientation, but does not constrain the tangential velocity. That is, it uniquely determines only the normal velocity. When gradient is zero, there are no constraints. In any case, further constraints are required to estimate both elements of the 2D velocity. Area-based regression. Smoothness assumption. 2D motion is smooth in the local image neighborhood of the point at which we are estimating the optical flow. For example, let's say we have gradient constraints at two adjacent pixels, x1 vector and x2 vector, which have the same velocity u vector. We will not satisfy all constraints exactly. Rather, we seek the velocity that minimizes the squared error in each, called the least square velocity estimate, where g of x, y is a low-pass window that helps give more weight to constraints at the center of the region. Solution: differentiate E with respect to u1, u2 and set to 0, as shown in the equations on screen. The constraints thus yield two linear equations for u1 and u2. In matrix notation, these normal equations and their solution are: assuming m to the power of minus 1 exists where area-based regression, the optical flow at each pixel, we can compute the components of the normal equations with a set of image operators. This is much preferred to looping over image pixels. Step 1. First compute 3 image gradients at time t corresponding to the gradient measurements. Step 2. Pointwise we can compute the quadratic functions of the derivative images. This produces 5 images equal to. Step 3. Blurring the quadratic images corresponds to the accumulation of local constraints under the spatial or spatiotemporal. This produces 5 images, each of which contains an element of the normal equations at a specific image location. Step 4. Compute the 2 images containing the components of optical flow at each pixel. This is given in closed form since the inverse of the normal matrix is easily expressed in closed form. Aperture problem. Even with the collection of constraints from within a region, the estimation will be undetermined when the matrix M is singular. Iterative estimation. The LS estimate minimized an approximate objective function since we linearize the image to obtain the gradient constraints. Nevertheless, the real objective function of interest is the estimation errors caused by this approximation are second order in the magnitude of the displacement. Iteration is used to decrease displacement's error in each step. These steps are: estimate the shift given the 2 images, warp one image toward the other. Image warps. Warping is not easy. Warp one image, take derivatives of the other so you don't need to recompute the gradient after each iteration. Often useful to low-pass filter the images before motion estimation for better derivative estimation and somewhat better linear approximations to image intensity. Aliasing. When a displacement between 2 frames is too large, that is, when a sinusoid is displaced a half wavelength or more, the input is aliased. This is caused by fast shutter speeds in most cameras. Aliasing often results in convergence to the wrong 2D optical flow as shown. Possible solutions. Prediction from previous estimates to pre-warp the next image. Use feature correspondence to establish rough initial match. Coarse to fine estimation. Progressive flow estimation from coarse to fine levels with Gaussian pyramids of the 2 images. High-order motion models. Constant flow model within an image neighborhood is often a poor model, especially when the regions become larger. These models often provide a more suitable model of local image deformation. Affine flow for an image region centered at location x0 vector is given by where a vector equals a1, a2 ... going up to a6 to the power of t, and then the gradient constraint becomes. So as above, the weighted least square solutions for a vector is given by a vector equals m to the power minus 1 B vector, where for weighting with the spatial window G, we get the equations: robust motion estimation, sources of heavy-tailed noise, outliers, peculiarities and highlights, JPEG artifacts, interlacing, motion blur, and multiple motions, occlusion boundaries, transparency, etc. Problem: least squares estimators are extremely sensitive to outliers. The error penalty function and influence function are displayed on screen. Solution: redescending error functions. For example, Giemann-Maclure help to reduce influence of outliers as shown on screen. Previous objective function, robust objective function, probabilistic motion estimation. Probabilistic formulations allow us to address issues of noisy measurements, confidence measures, and prior beliefs about the motion. Formulation: measurements of image derivatives, especially Ft, are noisy. Let's assume that spatial derivatives are accurate, but temporal derivative measurements have additive Gaussian noise as shown, where eta of x, y, t has a mean zero Gaussian density with variance sigma squared. Then given the gradient constraint equation, it follows that. So if we know u vector, then the probability of observing delta f vector, ft vector, is given by the equation. Assuming constraints at n pixels, each with 2D Gaussian noise, the joint likelihood is the product of the individual likelihoods, as shown. Optical estimation. Maximum likelihood. Maximum likelihood ML. Find the flow u vector that maximizes the probability of observing the data given u vector. Often we instead maximize the negative log likelihood as shown. Note, L is identical to our previous objective function E vector, except for the support g x, y and the constant term. Maximum a posteriori, MAP. Maximum a posteriori include prior beliefs P of u vector and use Bayes' rule to express the posterior flow distribution, as shown. For example, assume a Gaussian slow motion prior, then the flow that maximizes the posterior is given by where structure from motion. It is a range imaging technique. It refers to the process of estimating three-dimensional structures from two-dimensional image sequences, which may be coupled with local motion signals. It is an important subject in the fields of computer vision and visual perception. Structures in an image: edges, corners, lines, regions, points, etc. The SFM problem. Reconstruct scene geometry and camera two or more images. The SFM pipeline or block diagram can now be seen. Steps for structure from motion. Step 1. Track features. Detect good features, corners, line segments, find correspondences between frames, Lucas and Kinnaid style motion estimation, window-based correlation. The matrix on screen represents track features. Step 2. Estimate motion and structure. Step 3. Refine estimates. Step 4. Recover surfaces. Stereo reconstruction from two views. Epipolar geometry. Compute the fundamental matrix from the equation F equals K dash to the power minus T, F equals K dash to the power of minus T, matrix Tx, Rk to the power minus 1. Correspondence search. 1D search for corresponding points, x intersect x, or along epipolar line, L equals Fx. Structure and motion. Problem statement. Given two or more images of a scene, compute the scene structure and the camera motion. Assume internal calibration k, k dash. Assume scene is rigid. Start with two views only. Note, epipolar geometry is not known. Epipolar geometry. Epipolar geometry is the geometry of stereo vision. When two cameras view a 3D scene from two distinct positions, there are a number of geometric relations between the 3D points and their projections onto the 2D images that lead to constraints between the image points. Outline of structure and motion computation. Compute the fundamental matrix F from point correspondences. Xi tends to Xi dash. Compute the camera's motion from the fundamental matrix equations on screen. Compute the 3D structure Xi from the camera's P, P dash and point correspondences. Xi tends to Xi dash triangulation. What can be computed from point correspondences? Suppose we have computed x equals k dash to the power minus t matrix Tx r k to the power of minus 1. Can the motion be computed? F is the homogeneous matrix, so F equals k dash to the power minus t matrix Tx r k to the power of minus 1 equals k dash to the power minus t matrix lambda t x r k to the power of minus 1. The translation can only be determined up to scale. This is a consequence of the depth, speed ambiguity. Only the ratio of t and z can be computed, since if t tends to lambda t and z tends to lambda z, the images are unchanged. A large motion of a distant object and a small motion of a nearby object are indistinguishable. How many points correspondence are required? For n points, there are 3n unknowns, the 3D position of each point. For two views, there are 5 unknowns that are recoverable. Each point correspondence gives 4 measurements. For n points, expect a solution if 4n is greater or equal to 3n plus 5, that is, n is greater or equal to 5. Computing the fundamental matrix 8-point algorithm. Given n corresponding points, xi tends to xi dash, where I equals 1, 2, going on up to n. Compute the fundamental matrix F such that xi dash to the power t fxi equals 0, where I lies between 1 and n. The solution can be expressed by the following representations. A is an n into 9 measurement matrix and F is the fundamental matrix written as a 9 vector. For 8 points, A is an 8 into 9 matrix and F can be computed as a null vector of A. That is, F is determined up to scale. Note, this solution and those following does not require k, k dash. The 8-point algorithm least squares. Given n corresponding points, n is typically hundreds with noise on their measured positions. For n greater than 8-point correspondences, A is an n into 9 matrix as shown below. And in general, there will not be an exact solution to AF equals 0. A linear solution which minimizes mod of AF subject to mod of F equaling 1 is obtained from the eigenvector with least eigenvalue of a to the power t a. Epipolar constraint calibrated case is represented by the following diagram and equations, where E equals essential matrix, where E represents essential matrix. The vectors x, t and rx dash are coplanar. Ex dash is the epipolar line associated with x dash, where L equals E x dash. E to the power tx is the epipolar line associated with x. L dash equals E to the power tx. E dash equals 0 and E power t, E dash, E to the power of t, E equals 0. E is singular, rank 2, and E has 5 degrees of freedom. The skew symmetric matrix must have two singular values which are equal and another which is 0. The multiplication of the rotation matrix does not change the singular values, which means that also the essential matrix has two singular values which are equal and one which is 0. Decomposing the fundamental matrix, let us form the essential matrix as shown on screen. Compute T as left null vector of E, that is, e to the power of T equals 0. This determines T up to scale. Compute R from E. There are two solutions, R1 and R2. Set P equals K matrix I bar 0 for the first camera, and there are four solutions for the second camera as shown on the screen. The 3D point is only in front of both cameras in one case. SVD, the single value decomposition of E, can be arrived at as shown on the screen, where E equals U sigma V to the power T, which is to say E equals U diagonal 1, 1, 0 V to the power T. Determining cameras from the fundamental matrix. Algorithm for structure and motion. Building block is computing correspondences xj tends to xj dash and cameras p, p dash for an image pair via f as represented on screen. Compute interest points in each image. Compute point correspondences between consecutive image pairs. Extend and verify correspondences and cameras over image triplets. Extend correspondences and cameras over all images. Optimize over p to the power I, xj. Factorization. It is used to reduce the problems of structure from motion. This method is called Tomasi-Kinade factorization. Let us assume f equals image frames and n equals corresponding imaging points. The n points have fixed 3D coordinates xi, yi, zi, where I equals 1, n, which are expressed in unknown object coordinate system. Without loss of generality, we can make the assumption as shown on the screen. That is, origin of center of the object. In each of the f frames, the average depth of the points is about z0 and the range of depths is small relative to z0. Orthographic projection based on the above observation can now be seen. Let A be the image measurement matrix, which is constructed from the 2 cross 1 matrices xki, yki. Point y seen in the kth frame, k equals 1, going up to f. A is 2f cross n data matrix. Think of it as 2 f cross n matrices, one for the xki values and one for the yki values. Let Rk dash be the 2 cross 3 matrix, which is the first two rows of Rk. Then xki and yki matrix is given by. For any camera k, consider the average positions of the point. Applying equation to the right side, we get image measurement equations as shown on the screen. Thus, for each camera k, we can compute Rk tilde Ck, namely by taking the average of the xki, yki values over all I. We have two equations for each frame k, so we have stacked them to get a matrix product 2f cross n equals 2f cross 3 into 3 cross n. That is, we have a 2f cross n data matrix, left side, which is factored into the product of a matrix whose rows are the true x, y camera axes of the k cameras. This is known as the motion. And a matrix whose columns are the true 3D points written in scene coordinates, is known as a structure. To estimate these R' matrices as well as the points xi, yi, and zi, we decompose the data matrix A using the SVD A equals U A V to the power t, where U is 2f cross n and A is n cross n and V to the power t is n cross n. If the model were exact, then A would have rank 3, that is, only 3 of the singular values would be non-zero. The best rank 3 approximations may be obtained by keeping only the largest 3 singular values and their corresponding eigenvectors, as shown, where U is 2f by 3 matrix and A is 3 cross 3 matrix and V to the power t dash is 3 cross n matrix. As long as the ignored singular values are small, the column space of A will be approximately the same as the column space of U dash. Notice that the U dash matrix and the A dash V dash to the power t have the same dimensions as the rotation, motion, and XYZ structure matrices respectively. However, we cannot just assign these as our solution to the structure from motion problem. No reason why rows 2k-1 and 2k of U dash should be orthonormal, and we need the 2 rows of R-k to be orthonormal. To solve this problem, we find matrices that are close to the U dash matrices that are orthonormal. Let U2k-1 and U2k be the kth pair of 1 cross 3 rows of U. We want to choose Q such that the following orthonormality condition applies as shown. Let U2k-1 and U2k be the kth pair of 1 cross 3 rows of U dash. We want to choose such that the following orthonormality condition applies. It solves the nonlinear least squares problem. Even if we use the factorization on the right side of equation as shown, there is still an ambiguity since we can always insert any 3 cross 3 orthonormal matrix W in the expression as shown. Triangulation. Given corresponding measured, that is noisy feature points x and x dash and camera poses P and P dash, the problem is, in the presence of noise, back projected rays do not intersect, and measured points do not lie on corresponding epipolar lines. Objective. Given a sufficient number n of measurements, yi dash tends to yi, determine x such that yi dash equals x into yi. Then the algorithm can be stated as: set up linear equation system. M is the number of parameters as per the matrix shown. If B is 0, solve with SVD, else solve with pseudo-inverse, and determine capital X from small x. The equation for one camera view can be expressed as shown. The stack equations for all camera views can be expressed as A matrix X equals 0, where A ranges from A1 going up to AN. This minimizes the algebraic error, and no geometrical interpretation can be deduced. X has 3 DOF, 4 parameters due to homogeneous representation. One camera view gives 2 linearly independent equations. 2 camera views are sufficient for a minimal solution. Solution for X is eigenvector a to the power of Ta corresponding to smallest eigenvalue. Homogenized solution for X to obtain the Euclidean vector as shown. Bundle adjustment works by minimizing a cost function that is related to a weighted sum of squared reprojection errors. Problem definition. The goal of bundle adjustment is to determine an optimal estimate of a set of parameters theta given a set of noisy observations. Most bundle parameters cannot be observed directly. For example, projection matrices, 3D point coordinates. Instead, they allow us to make predictions of quantities that can be observed directly, such as the measured pixel coordinates of imaged 3D points. Let the set of predictions be z theta and the set of corresponding observations be z dash. Then residual prediction error delta z is given by delta z equals z minus z theta. In general, the observation vector z may be partitioned into a set of statistically independent measurements, z1 going up to zn, with associated predictions z1 theta going up to zn theta. Bundle adjustment proceeds by minimizing an approximate cost function. For a maximum likelihood parameter estimate, the cost function should reflect the likelihood of the residual delta z. Under the assumption of Gaussian distributed measurement noise, the appropriate cost function is a sum of squared errors, as shown. Here, delta zi theta is the feature prediction error and wi is a symmetric positive definite weight matrix that is chosen to approximate the inverse covariance of the measurement noise associated with measurement delta z. Numerical optimization. Newton's method. It is an iteration process. At each iteration, we seek a parameter displacement theta tends to theta plus del theta that minimizes the function of theta. By fitting a Taylor expansion-based local model to the cost function, it is possible to solve approximately for theta using linear algebraic equations as shown. The Gaussian-Newton approximation method. Differentiating the weighted sum of squared errors cost function in equation gives the Hessian and gradient in terms of the Jacobian expressions as shown on screen. The Newton step prediction equations become the Gauss-Newton or normal equation as shown. Parameterization. In practice, the rate of convergence depends critically on the quality of this approximation. Thus, it is important to choose a parameter representation such that the effect of parameter variation will be locally as near as linear as possible on the chosen cost model. An interesting problem is to parameterize camera orientations in such a way as to avoid the familiar singularities associated with Euler angle representations. The 3x3 rotation matrix is expressed using the Rodriguez formula as shown on the screen. Step control. Newton's method may fail to converge to a minimum cost solution. It can converge to a saddle point instead of a minimum, and for large steps, the quadratic cost model may be so inaccurate that the cost will actually increase. To guarantee convergence, a suitable step control policy must be added. Each step must follow a descent direction, that is, a direction with a non-negligible downhill cost component, or if the gradient is near saddle point, down a negative curvature direction of the Hessian. Levenberg-Marquardt works by replacing the Hessian h in the Newton step equation as shown. The complete procedure for step control is now shown on the screen. The final stage of most algorithms is a bundle adjustment, which is used iteratively to refine structure and motion parameters to achieve a maximum likelihood estimate by the minimization of an appropriate cost function. Conclusion. In this chapter, we have covered the following in detail: regularization theory, optical computation, motion estimation, structure from motion.